Okay, and then that's good. And then I'll start it up on mine. And we'll see how that works.
We cannot get access to the Colab slides.
Not yet. Share them. I think ask these guys if they want to take complex functions better. Uh, yeah, please come, have a seat, sit down.
When I first started Eve, I was a minor, and I was really tired.
Okay, and let me just log in here. Testing, okay. Start the virtual camera, start recording. And select the window on the left. Yep, just give me a second. That was done last week. Myself, turn on the camera. So what I want to do. No, so I guess. Okay, so that didn't work so well. So I can record, but I have to mute myself when I connect. That should be okay, okay, so I need to. Test. Yeah. Okay, so why is that? Because I need to deafen, and I can do this, and then I can record, and then maybe I can go. Okay, and I can share my screen. Okay, good. Okay, so welcome to the class. Before we start, for the people that are here for the first day, you will have to join the Discord channel. where we will have the classes online and also publish our lecture notes and things like that. Now, you want to join the complex motion planning channel on my Discord server. And the URL is as follows. So first of all, create a Discord account if you don't have it yet, and then join this particular channel. So is everybody signed in? Did you guys connect on Discord? Yeah. Okay. And you can see the complex motion planning server and join it. So if I post a message on there, you will get it. Okay, good. Then today we're going to start with the introductions. I'm going to talk a little bit about myself and my research, but for the rest of you, I'll give you a chance to introduce yourself, including your name, your university background, your programming, robotics, AI experience, things like do you know C++, Python, what programming languages you know, develop a self-driving car, what projects you've done, your hobbies, and the best book that you read or movie that you watched in the last 4 weeks. So what was the book or movie that you enjoyed the most? And you can introduce yourself to your fellow students after my little introduction here. The other thing that we discussed last time, but I'm just going to repeat it so that everybody is on the same page. The assessment for the course consists of a 20% assignment. %20 midterm, 20% project, and 40% final exams. Now, the project will be joint collaboration or joint group with students from Germany. And I'll talk a little bit more about that. Basically, this course will be part of the Global Virtual Classroom that they organized here at NTNU. Starting March 11th, our lectures will be joined by Professor Gernt and his students from Westphalia University in Germany. There will be then part of the lectures will be given by Professor Gernt to all the students. Part of the lectures will be given by me, depending on the topic. And then at the end of the 6 classes that we will have jointly, minimum of 6 classes we'll have jointly. But I think probably it'll be more like 7 or 8. There will be a project. The project will be using the Turtlebot platform, which is a simple differential drive robot. And come on in for motion planning. Yeah. Okay. Come sit down and make sure that you log in to this Discord channel. Join the complex motion planning chat. So the joint classes should be quite a bit of fun. You get to know some students from Germany, see what problems they have with their studies. You can swap war stories or horror stories about your education here, and see what their views are. We did it last term with the computer vision class, and turned out to be quite successful and quite a bit of fun. So we'll do it again this term. That means that the last year it was pretty hard for the Taiwanese students because the joint lectures started at 11 p.m. in the evening. This time we swapped it so that the German students have to start at 8 a.m. So last year the Taiwanese students were mad at me for starting the lectures too late, and this time the German students are mad at me for starting the lectures too early. 8 a.m. German time will be 4 p.m. our time here. So for the Taiwanese students, it's easier. It actually overlaps with some of our lecture time. So my name is J.P. Maltes, and just a little bit of background about myself. I was born in Germany, then did my PhD at the University of Calgary in Canada, where I did an AI planning system, motion planning system. and the problem-solving system, and that worked quite well. But then when I started my first job at the University of Auckland in New Zealand, I realized that the kitchen robot that I developed was, in a sense, pretty smart. It could use different kinds of problem-solving strategies, but it was all based on simulation only. And if I change the simulation just slightly, you can greatly modify, change the performance of your AI planning system. So for example, one of the research topics and benchmark problems that people used for AI at that time is called the blocks world. The blocks world is a very simple domain where you have equally sized blocks that are labeled. So for example, you have A, B, C. Right? And then you ask the system to build another kind of configuration. So maybe you want A, C, and B, right? That will be your target configuration. You want to, and you have a robot that can pick up one block at a time and put it down. Now, the way that happens is that you would think the representation and the logic is quite straightforward, and in a sense it is. But this particular, even though it's a very simple domain, right, it's much simpler than what our robots have to solve if you want to have a real robot perform something useful in the world. If you now write a simulation and you implement this, then basically you develop some operators like pickup. And it means you want to pick up block A, block X from block Y. Right? Like here, if I want to do this task, I want to pick up A from B and put, then the next thing then would be put A down on the table. So we have put down, block X on something Y, on some other block, right? Where X and Y are variables. So that makes sense and describes the domain, and you can then run your planning system. But you can make your planner run a lot faster if you're smart and you tell the system that X can never be equal to Y. Because then it'll not even try these instantiations. But if you don't tell it that, then the robot, the AI agent will try to pick up block A from block A, because it will try and find all the different ways of instantiating the variables here. So it'll try pick up block A from block A, which doesn't make sense, right? There's no way that you can pick up a block from itself. So if you don't tell that to the system, it basically tries in order to solve it then, it tries all the different combinations. So A from B, A from C, B from A, B from C, C from A, C from B. Those are all, it has to consider all of these, right? But if you apply this one here, then AA it will already reject, BB will already reject, and CC will already be rejected. So that means instead of 1, 2, 3, 4, 5, 6, 7, 8, 9, you only have 6 configurations. So now your branching factor is reduced by 30%. So that makes a huge impact on your runtime. But none of the simulations tell you exactly whether they're actually doing this or not. So some planners may run faster, not because the planning system is smarter, but they may run faster because the simulation helps them in some way like that. So that's why with when I started, I decided that really if you want to make sure that your AI research is relevant, it's not just based on different castles in the sky simulations where you get everything to work, and you can add additional knowledge secretly without anybody else noticing it, right? If you do that, then you have to do it in the real world, which is why I got interested in robotics. And then we started with our first robot systems. No, this is not. This is our latest robot system. So this is where we are now. One of our early systems. This one, for example, this one is not actually the very first one. I showed the other video already last time. So here we have a little global vision system, so a camera mounted overlooking the entire playing field. And then toy car, remote control toy car that we bought from the department store that we connected up to the parallel port of a computer. And this particular project or assignment was based on a movie called Wages of Fear, which is a very famous French movie from the 1950s or 60s. In that movie, the truck drivers have to pick up the nitroglycerin, drive back over the Andes mountain, and then deliver it to the oil refinery. So here the robot had to drive over our small mountain, admittedly, and pick up the nitroglycerin, the block, and then drive to the second robot arm, our oil refinery, and now the oil refinery is going to pick up the object. So that was a pretty nice assignment. Included quite a bit of planning at different levels. You needed to figure out where to drive the robot first. You needed to do path planning, then some motion planning for the robot arms in order to put the.
So you can download the book from here.
Who is that?
Which gives you some more background if you're interested in it.
Oh, that's me. Okay. Because it starts the second video. Yeah. So that's how we started. Quite a bit of fun. Now, the thing is, compared to just driving on the flat surface, even this little mountain here, right, which for a human wouldn't cause any problem, made the whole assignment a lot more difficult because if you have a remote control and you tune your car to drive nice and slow on the straightaway, if you then try and go up the hill, it will get stuck, Right? It just won't move anymore because you don't generate enough torque to overcome gravity. You need more torque to go up the hill, right? So then the students increased the speed at which the robot moved, which was okay until you drive downhill. And that's why we actually have the little gate there, because at the beginning, students had very poor velocity control of the robot, and the robot would just shoot out of the playing field much too fast. Right? If you do this in a simple simulator, you never even consider gravity. If you have a more complex simulator, yes, they actually include gravity, but then you have other issues that are not often ignored. So here, this is another Global Vision project that we implemented that I liked a lot. This is actually Pac-Man. So we have real robots driving on top of the television. And the television does the dots and the strawberries and everything. So now we ate the strawberries, so now we chase the ghost. And if you look at the performance, then you see that the Pac-Man actually works quite nice. It eats the dots and everything. But this robot, our Ghost, which was programmed by different teams, so it was an adversarial game. In this case, the Ghost doesn't seem to be performing so well. So this was kind of funny because there, the robot actually drove backwards the Pac-Man. Usually the Pac-Man can only go forward, but we didn't put that in. So in this case, the Pac-Man also can drive backwards. But now he got caught and it's game over. The main difference, that actually when most of the teams, when we started, at the start when we did the competition, everybody thought that this particular team would win because they had very nice control over the preceding days. All their testing went really well, and everybody thought that team would do really well. Now they made one change, which is why their robot didn't perform so well. Any guesses of what they changed? The only thing they did was they had the robot used, they used the robot for a couple of days. Then they thought before the competition we should put in new batteries. Just so that that we don't run out of power during the competition, right? So most of the time they were using sort of average middle charged batteries. Then they needed, when you control these on the remote control, of course, these are very simple robots, right? They're basically what you get in a toy. So you can turn left, you can turn right, you can go forward, you can go backwards. And they're only even digital controls, so you cannot even say 50% forward or 100%. You can only say go forward, go back, go left, go right. And backwards left, backwards right, forward left, forward right. Those are the options that you have. So button control. And so we cannot say turn by 10 degrees. All we can do is we can turn on and say turn, start turning. And then at some point in time, we need to tell it to stop and then say go straight forward now. But if your batteries are not fully charged, then the velocity that the robot drives is quite a bit slower than if you have fully charged batteries. Which is why, if you look at the behavior of the robot, it's actually turning in the right direction and trying to do the right thing, but it's simply overturning all the time, right? And students at the beginning didn't know what was going on with their system until they figured out. It took them a while to figure that out. So that tells you, in a real robot system, you also always need to make sure that you have a very good debugger view or a testing view so they can figure out what's wrong. And the other thing is that none of the simulators that you use in Gazebo, the Kokomo and Colabo and all of that, Isaac, Jim, none of them model the amount of charge in your battery, because nobody thinks that that's an important feature. But it can completely destroy your performance, even if you just go from halfway charged batteries to fully charged batteries. And until you really do work with robots, you never worry about the battery charge. It's just some constant amount of power that you should get. Unfortunately, in reality, it's very different. So then, for the next assignment, students were implementing feverishly methods to automatically tune the turning and estimate the velocity at which the robot turns. Something that nobody that implements a robot system in a simulation thinks that's even useful. But in reality, yes, it's very useful. Because even if you say, okay, fine, I know, then I just need to measure the battery voltage. But if you measure the voltage, that doesn't tell you how much current the battery can deliver. Until the very end, the voltage drops. So, that's just another example of how important it is to do things in the real world. And then we have been doing, since 2002, I moved back to the I moved back to Canada, to the University of Manitoba in Winnipeg. And since then, I've been working mostly on humanoid robots. But I do like the competitions for robots. I think that's an excellent way to benchmark our research, to show progress. And I'll just show two quick videos. Here's the one from the spring.
要让百留下好印象，要有好思绪。赛程有22种关键营养素，增量不意外，让你思绪清晰，好灵光。
So here's the, we take part in this international competition of teams from all over the world with the humanoid robots. One of the things that we have to do is a sprint. Actually, they have to do a decathlon, the humanoid robots. So they have to do 10 different events. So here's a false start, so we have to pull the robot back. So one nice thing about doing sports as a benchmark for robotics is that if I say we're doing a sprint, then everybody understands what we're trying to do. We're trying to measure maximum speed on a short distance. To make it a bit more interesting, robots have to walk forward and backwards, and there's some subtle differences between those two. The other nice thing is that you can keep records. So the world record for this sprint was 1 minute and 7 seconds in 2012, and is now in 23 seconds. So you can see how much the So there's a whole bunch of different sports, and we're doing soccer, the sprint, the marathon, which is running outdoors, 425 meters, archery, like shoot bow and arrow, basketball, the Spartan race. That one I like because in 2019, my team was the first one to actually climb the rope. So I thought that was really cool to have the humanoid robot climb up a rope. And other events, the mini DRC, which is kind of like a rescue robot scenario that is teleoperated, and weightlifting. I think I missed. Now, we also run a number, and part of the Spartan race competition is the wall climbing, and for this particular course, complex motion planning course, one of the things that I want to do is to implement a high-level simulation of a rock climbing robot. So the problem that we're trying to solve with our humanoids in this course is like this. So the robot has to plan how to climb up to the top of the wall. This was done with some students from Germany, some of my students from Germany. And this is very interesting from a research point of view because of the infinite variability of the environment. The robot has to be able to plan all its motions online. For soccer, for example, you only need a dozen motions. You need to be able to walk forward and backwards, and move to the left, and move to the right, and turn left, and turn right, and kick with the right foot, kick with the left foot, that kind of thing. If you have those, then those are all the motions you need ever in your soccer match. But here, huge variation, so you won't be able to pre-program all the motions. So that's why I think it's pretty interesting, and of course, eventually, with this research, we want to try and do some climbing like this. So bouldering or rock climbing is pretty popular nowadays as a sport for humans. So we're trying to do something like that with our robots. But here, this shows you this sort of explains why you won't be able to pre-program those motions, right? You have no idea where the boulders are. Right, so up and backwards and over, and it's just basically almost an infinite variability of what motions you can do. And of course, if you can implement your robot and it can do that, then you will immediately get professor position at MIT or anywhere else you want. Like, there's no way that we'll be able to finish that in our course, but we'll try and push in that direction, making small steps toward the achievement of that goal. So there you go. And the interesting thing from an AI researcher point of view is that nobody thinks that rock climbers are intelligent, right? You don't think that they are geniuses. Chess players are intelligent, Go players are intelligent, lawyers are intelligent, doctors are intelligent, but rock climbing, no. But in fact, when you look at the complexity of the domain, and you look at the performance of computers, then chess, we already beat in 1996. There isn't a person in the world that can beat the best chess programs. More importantly, any one of you guys, if I set the assignment to implement a chess playing program, and I'll tell you a little bit about A-star search and taboo search and a couple of tricks for representing a chessboard on a computer, any one of you can implement a program to play chess that plays better than 80% of the people in the world. Because most people are just very bad at playing chess. They're not anywhere near the world championship level. Similarly for Go, 2016, AlphaGo beat the human world champion in chess. And since then, our deep learning systems have all improved, but human brains don't evolve so quickly. Medical diagnosis, we can match the best doctors. We can do case law, case-based reasoning, case law, very well, just as good as the best human experts. But we're very, very far away from even recognizing whether there is a foothold or a handhold or what. So even the perception problem alone for rock climbing would be brutally hard. And the motion planning problem is much, much harder. And the reason for that is that, and the reason why we don't think it requires intelligence is that in order to play chess well, you need to do a lot of bookkeeping in an abstract space, right? You need to think about the positions on the chessboard, how they will evolve. And that's something that the human brain is not very good at. But computers are really, really good at that. Right? Computer can just store in memory that part of the playing field, that part of the chessboard. So they're very, very good at that. But humans are very bad at that. And in a sense, it makes sense from an evolutionary point of view because human species, Homo sapiens, is about 200,000 years old. Our first human remains from Homo sapiens were found in Ethiopia, Lucy. And for most of the time of our abstract reasoning capabilities have developed very, very late compared to all our other skills. Writing, right? The first writing is about the Sumerians about 4,000 years ago. So that means 196,000 years of our existence as the human species, we weren't worried about playing chess or anything like that. We were worried about interpreting the three-dimensional world around us and being able to move through the three-dimensional world around us. Being able to recognize that this particular pattern in the jungle belongs to a tiger. If you walk in front of it, not very good unless you want to act as food for the tiger. This is a deer. Deers you can hunt, you can eat them, right? So the vast majority of our brain has deal with problems like perception, recognition of natural scenes, planning motions, moving our bodies the way that we want them to do, making sure we don't fall over, recognizing that this is a cliff. If you step on there, that rock is loose. It's going to slide and you're going to fall to your death. That kind of reasoning. And we have no idea how the brain does it, and our computer approaches to that are much worse than world level performance or Olympic level performance in the rock climbing or anything like that. We're very far away from the performance of a 3-year-old when it comes to, or a little baby when it comes to recognizing faces, mother and father and parents. Little babies can recognize 100% accurately. AI systems can recognize all kinds of things, but make much more mistakes. But because it's subconscious, because it's what our brains are really good at, nobody gives these athletes enough credit for also being quite intelligent in order to be able to work out these motion plans. And of course, they also have to practice a lot, many years before their body can perform these different tasks. And lastly, one other thing that we do with our robots is the Robot Magic Show, which is kind of fun. So we develop robots that can do magic tricks. So here's one that we implemented. We actually won the competition with that. It's a coin behind the back trick. So it asks you to bring the hands to the front with the coins in it, then it's trying to guess which hand the coin is in. And then actually detected it correctly. This is actually interesting because it combines computer science, AI, and psychology. Some magicians figured out if you ask people to cross their hands 80% of the time, the hand with the coin will be on the bottom. So that's why I asked the person to cross the arms. And then so that part was trivial, figuring out that we want to look for the bottom arm. Figuring out which arm is on the bottom was the hard part. It took us about 3 months to do that. We tried to use vision. We wanted to use just vision alone because for a person it's very easy which arm is on top. Right? You know the left one. No question about that. But to implement a computer program that can do that, it turns out to be quite hard. So we never were really successful with vision alone. There are PulseNet and BodyNet and estimators for the pulse of a human. They also work well, but they don't know which arm is on top. They just know that one arm is here, one hand is there, and one elbow is there. And one hand is there and one elbow is there, but they don't know if it's like this or like that. And so it took us, we tried a lot using vision alone. That didn't work, so eventually we ended up, because our robot has a LiDAR scanner built in, so it just uses the LiDAR scanner to scan the person, and you can see the point cloud here. And was the interesting thing with this particular thing is we had one of the volunteers during the official competition, so we weren't cheating, we were taking a real volunteer. There you can see the point cloud. So this is during the judging of the actual competition. The first part of the video was during the industrial exhibition, like afterwards the gala presentation. And then, so then it actually guessed correctly, and the guy was convinced that our robot was using mind hallucinations to force him to move that arm below. So he thought that our robot had psychic powers to be able to dominate human brains in which arm goes where. And I said, well, if we could do that, then of course we don't need any shake or anything like that. And if, think about it, if the robot forces you to put this arm on the bottom, right? Our goal is to find out where the coin is, correct? So it's here, I want to find out which arm the coin is in. So if I then have the psychic ability to move this arm to the bottom and this one arm on top, then I don't actually need to do that because I need to know that the coin is in here, right? Which means I already knew where the coin is, so then I don't need to ask you to move anything. But he just didn't believe it. No, because the robot did it like this, that's why I did it like that too. I'm like, yeah, but at the end of the day, we would have, this was in Macau, which is famous for gambling, so we could have made quite a bit of money with gambling with people. Okay, good. So that's about my research. I'll show some other videos later on throughout the course. But now it's up to you, so we'll go with your name, your university background, first year master's at NTU, or before I was at NTUST or something like that. Then your background in programming, AI, robotics, so in particular C++, Python, what programming languages you know, what projects you've done, your hobbies, what you like to do in your free time, and the best book or movie that you read or viewed in the last month. And then we'll start with you. Yeah, right now.
And my university background is NTNU Basics.
And now you're a master's student or bachelor?
PhD.
Now you're a PhD student, okay.
And program experience Python. Will be Python basic.
For how long? How many years?
Learn in university for 1 year.
Okay.
My hobby is play volleyball.
Okay.
That movie, I watch the Spy Family that long.
Okay.
Okay.
Good. Thanks.
My name is Paul Michel, and I am NTNU University physics. Yes. And my program is experiment is Python and MATLAB.
Okay. Yeah.
And I use Python I have used Python for 6 years. Only do some GUI for experimental instrument.
Your hobbies? Hobbies and the best book or movie.
No. Hobbies. Running.
Running? Okay. Yeah. What kind of running? Marathon or short, middle distance or sprint?
Long.
Long distance. Yeah. Okay. Good. Thanks. Next.
My name is Xie Dongjun, and I have NTNU Master of Physics, and my program experience is Python, and I use Python to only complete my course.
Mm-hmm. Okay. Your hobbies and the best book that you read or the best movie that you watched in the last 4 weeks. Hobbies?
My hobby is watch some movie, like
Like what?
Korean
Korean movie.
Yeah.
Okay. Yeah, Korean movies are very popular right now. Sure. Yeah. Okay. Thanks. Next up, you.
I'm Tyler, 中文名是王立尚. I'm graduated from NTNU Electrical Engineering, and I'm now the second year master degree of NTNU Electrical Engineering. And let me share about something different with Denmark.
Actually, talk about your programming experience.
Yes. Actually, I have some experience about commercial development and some XR, AR, VR, that kind of development. And I have some experience in social media application. Yeah, so that is completely fine. And I also have some experience in computer graphics, which is you use a simple matrix to draw a sphere in the 3D space just with mathematics. And my hobby is software architecture design. Yeah, it's another hobby I couldn't share.
Okay.
Yeah, because I like to solve the problems that I can design the software extensive to field. Yeah. So it can be extended without change some details. Mm-hmm. Yeah. So the best movie, no, I seldom see movie. The best book, the Bible.
Okay. Yeah. Good. Thanks. Next up.
I'm Tony, and I'm from NTNU, and right now I'm in JP's lab, which is doing research with robotics. And programming, I use Python. And hobbies, I like to go to gym or go hiking on some mountain and relax like that. But best books and movies, I haven't watched it recently, so I don't really know which one it is.
Okay. Good. Next up.
Hello, my name is Steven. My graduate from NTNU, and programming experience Python, Java, and HTML. And my hobby is play video games. And best movie is last 4 weeks. I see Taiwan movies and two that I see a Taiwan movie and Chinese New Year, but I don't like this movie. Yeah. And this movie is his name is Huang Qian. Yeah. Pay back of money. Okay.
Okay, so not recommended. Okay, next up.
Hi everyone, my name is Hans, and I'm a third year undergrad student at UTSC. I'm in the mechanical engineering program, but I'm taking like the English program, so it's international. So it's all in English. Experience in programming, I enrolled in a fundamental C++ course. I took a.
Did you pass it?
Yeah, I passed it.
Yeah, okay.
Yeah, and then I passed the basic Python course. We were our final project was to like use like a gyroscope, and use machine learning to identify moving motion. Yeah, but it's kind of just pretty simple. Just like a gyroscope, and then you move it around to determine like which position it is at. And last semester, for my lab class, I was told to work on a line follower robot, which uses Arduino. Yeah. But it didn't really work that well.
Okay.
Hobbies, I like playing instruments and I like reading books. And best movie in the last month was
Movie or book, depending on
movie or book. Maybe movie. My Dinner with Andre. Yeah.
Your what?
My Dinner with Andre. That's the title of the movie.
Okay, good. Yep, thanks.
Hello everyone, my name is Tuan. I'm from Vietnam, and in university I'm a first year student for undergraduate at the USD. My major is also mechanical engineering. About programming language, I know Python and a little bit about C++. Hobbies, I like playing games and watching movies. I think my favorite movie is the movie named Real Steel by the robot fighting Real Steel. Yeah. I really love that movie, and the series movie I like to watch is X-Men.
Okay. Yeah.
The best book I think I read there's a book of a French novel called Without Family of Hector Macron. I really love that book. I think that's the best one I have read so far.
Okay, I'll have to check that out. I like to read books.
Okay.
The last book that I read, in the previous class I asked about the last book that I read. That was Glenn Cooper, one of his fat thing. So that one is a fantasy story about wizards and elves and dwarves, and but it is written in the style of a detective story. So there's a dead person, then they have to investigate. So that was quite a bit of fun to read. Because I forgot to say about my books, or the last book that I read. Okay, good. That's it for today for our delegation from the physics department. Does any one of you guys do quantum optics? What kind of physics do you do? Quantum memory and quantum computing. You actually work on quantum computers? Okay. You building one? Because quantum computers, like everything that I talk about here, with respect to complexity, quantum computers are sort of, if they ever work, they basically make the whole field of AI useless, because then the very simple algorithm that would lead to an astronomical complexity runtime, quantum computers can basically execute an infinite number of programming steps every clock cycle. And of course, if you can do an infinite amount of computation, then every computation will just take one clock cycle. So then all of AI would be totally changed, like overnight, right? The problem is to get enough bits to be able to represent enough quantum bits and entangled bits in order to be able to represent that. But you should pay attention because this term, this summer, we're organizing a student exchange with students from the Technical University in Darmstadt in Germany, and the vice president of that university is a good friend and colleague of mine, and he's actually a very excellent physicist, but he does quantum optics. And their recent project, one project that they had, which I thought was really cool, was they could fly the helicopter and then shoot a laser, because everything he does is using lasers. And they can shoot a laser into the ocean, and then they can measure on centimeter scale, they can measure the water temperature based on, he told me it's some kind of radiation that if the laser is powerful enough, it generates this radiation, which basically measures the speed of sound at that temperature, at that depth. And it has to go very, very fast, right? And so they developed the electronics to do that. And right now he actually has demonstrated the quantum encryption. So right now he's doing a project with the German Telekom to do quantum encrypted circuits between 4 different places in Germany. And quantum encryption would be kind of important because you could notice if somebody actually is eavesdropping or not on your communication. So that would change a lot of things. So if you're interested in going to Germany for that, then you need to discuss it with me, because some of my students are going there for the robot competition at the same time. And we have a MOU with that. So today, what I want to do is look at motion planning from a very high level point of view. And that means we assume that we have a capable robot that can pick up and put things down reasonably well, and we want to implement a motion planner for the Dr. Eureka game. So watch the game description here.
What's the best part of science class? Okay. Chemistry. For me, it was really the experiments. Let's kind of mix them together. Okay, well, I like mixing chemicals. Is that fun? Yes. Mixing things together to see what happens? Yes. Mixing vinegar and baking soda? Okay, that's what you're doing in this game. You're taking vials of marbles and mixing them together. Basically, you're rearranging marbles. It's that old, if you're 5 gallons in this one and 2 gallons in this one. It's the same thing, but with colored marbles addition.
So you start out this game with having 3 tubes, right? 2 green balls, 2 red balls, 2 blue balls, or purple balls.
So we got 3 of these vials. These are pretty strong plastic vials. They come with these balls which look very much like gumballs. So we have 2 purples, 2 reds, and 2 greens. And we have a stack of cards, and we'll table, so we're going to turn one of these cards like this. So this is going to be a purple green, a green red, a purple, and a red. So let's put this back here so we can see what I'm going for.
And so that would be, you have these different cards. There's all kinds of target configurations configurations. So now you have to generate this setting. Green, blue, red, green, and red, blue. But you're not allowed to just pick out the balls and then say, okay, here, this one, this one, this one, this one, right? The only thing you're allowed to do is pour the balls from one tube into the other, right? Kind of, and you're supposed to resemble doing a chemical experiment.
And then you're going to use these like try to get those numbers. You're not allowed to touch the balls with your fingers at all. The balls are allowed to touch the paper at all. So maybe I would do something like this. I would put a green one like that, and then a purple one in here. So there I got.
So now he has the purple on the bottom.
And the purple on red. Let's put those there. And the purple and the red here. And then the green and the red together. There we go. Now let's get things in order, like this. And you say in the pencil, the green, the purple, and the red and the purple are incorrect. But we are allowed to do this at the end.
So that's one special part of the game. You can actually flip the entire tube over if you want to.
Yes, I'm correct. If I'm the first person to do that, I'll get the card. We then turn everything right side up, blue and blue as regular, and we go to the next card. So the next card here has 3, 1, and 2. And I have to rattle with that one. Or perhaps it will have some like this. 3, nothing, and 3. Sometimes it even has this one. 4, 1, and 1. So there's all sorts of combinations, and they're all playing with you at the same time. Pulling these in. If you ever wanted to go and touch a ball, you would have to basically say, I'm not of this round, and wait till the next round before you can start over again. The first person to get who wins 5 cards is the winner of the game.
Yeah, so every time you're the fastest to get it, then you get the card, and at the end of the game, the one that has the most cards is the winner.
In the right order, and now you get to touch them for women. I like how it actually makes me want to do the science experiments, and it was a little difficult for me to like do it really
It didn't help that someone kept shouting out about guys and someone's model to the grader.
That was you.
So that's the game that we want to implement on our robot, and hopefully we'll be able to do that faster than a human can do it. Now, if you look at it, if your professor gives you that particular task, right, then for human, what would they worry about? What would they focus on for playing Dr. Eureka? The steps, right? Like this tube 2, 2 balls into tube 3, 1 ball into tube 1, then 2 balls into this tube. So they would worry about the order and the operations, the pouring 8 actions that they need to execute, right? None of them is going to worry about holding the tubes, not letting the tubes drop. Tilting the tube so that the ball rolls out. Right? You can see it's actually not that easy. We have the game in the lab. You can try it yourself if you want to. You have to be a little bit careful, but if you have normal eye-hand coordination, this is not a problem. If you implement this on the computer, 90% of your time will be spent on trying to pick up the tube, tilting the tube, making the ball go from one to the other. Here's this is not actually the latest one. Check what the latest one is with our Thorman, because that one actually does look a lot better. But here, yes. This is oh, so one of the things is we had to detect the vision processing. Oh, maybe it is the one. Because we need to detect the cards obviously correctly so that we can move it to the correct target position. And this is our latest system that we have. So we show the card to the robot, and then we put the tubes on it. And the Arupo markers, if you know those, that's where we tell the robot what the playing field is like. And here we wanted to pour 2 balls, but it's hard to pour 2 balls and control the velocity, so it does 1 ball, then 2 balls. So if you want to play this against humans, that's one thing that you could definitely improve your speed, right? And by the way, this video is sped up by a factor of 2, so it's twice as fast as real time, otherwise it would take even longer. And I think that's it. That's the target configuration that was on the card. Oh, not yet. And then that was the target configuration for our robot, so it can solve it, but we would like it to do that faster. Actually, we beat some children playing that game, but we were cheating a little bit. I'll tell you later on how we were cheating. So now, of course, you can clearly see there's two different levels of motion planning that we need to consider ourselves with. One is sort of the abstract level, which is more the AI task planning problem, where we need to make the moves that this ball, two balls from 2 to 3, one ball from 3 into 1. And then there's the motion planning component, which is the part where we actually have to move the joints to be able to pick up the tubes and to put the tubes down and to pour one ball or two balls. Things like that. So today, as a warm-up, we'll just worry about the task level problem. So we can model that as a state space search problem, where we start out with our tubes, and we have 2 red, 2 green, and I know that they're really purple, but I'll just call them blue to keep it with RGB. And then we have a goal configuration. Red, green, red, blue, green, for example. And that's what we want to generate. And show to the user. So now if we look at that as one state of our system, there's many features of the tubes that are important for the lower level motion planning, but are not important for this particular task planning problem. It doesn't matter whether the tubes are 1 centimeter or 2 centimeters wide. It doesn't matter how big the balls are. It doesn't matter how tall the tubes are. Right? So if I want to describe the state of the problem, which is the level that humans are concerned about this particular problem, then I really only need the number of balls in each one of those tubes. So we can consider this one state. We're doing search-based planning. There's different types of search-based plannings you can do. The simplest one is to use the state itself, so state-based planning. So the state will be described by the configuration of the balls in the tubes. Now, then from each state we have various actions. So what kind of actions do I have coming out of this state? Not how many, just name a couple of them, some examples. Put the red ball to the green one. So that would be R, G, G, B, B, right? That's what you meant? That's certainly one of the things I could do, right? And in fact, I can call that tour 1 from tube 1, tube 2, tube 3, tour 1 from tube 1 to tube 2. I can even give it a name that makes sense to people. Right? What are some other ones? Draw them smaller. What other actions can I do? For what? For 2 from 2 to 3, yeah? And then that would give me RR empty and GGBB, right? Okay, that's good. Then one more example. For 3 to 1. For how many from 3 to 1? 1, okay. So for 1 from T3 to T1, that would give me BRR GGB, right? Okay, yeah, those are all nice states, nice actions. Then the question is, what is the total number of what's the total number of actions I can execute from that particular state? Six. Why 6? Correct. So I can either move 1 ball or 2 balls, yes, and then I can move from here to there, T1 to T2 or T1 to T3, right? And that's different from T2 into T1 and T2 into T3, right? And T3 into T1, T3 into T2. So here, the different 2 configurations, I have already 6 possibilities, right? 1 to 2 or 1 to 3, 2 to 1 or 2 to 3, or 3 into 1, 3 into 2. So I already have 6 possibilities there, and then I can pick whether I want to move 1 ball or 2 balls in that configuration. So I already have a minimum of 12 different actions, right? So here we would have a minimum of 12 from this configuration. However, different states will have different number of possibilities there. If I have 3 balls, red, green, blue, right, and green and red, green, blue, so green and blue and red, for example. Then I have how many possibilities? I can move the green one. I can move, so here for the green one, I would have 1 option. I still have a total of 6 different possibilities. But for the green one, I can only move 1. Right? Here I have 3 possibilities. Because I can move 1 ball, 2 balls, or 3 balls. And then here I have 2 possibilities, I think. So here I have 6 possibilities, which is the same as the 2 by 2 by 2. I would also have 6. Configurations. So I have 3 times 2 plus 1 times 2 plus 2 times 2. So here, this is multiplied by 2 because for each one of those I have 2 possible other states that I can move to. So this would also be 12. If I have it's 3 plus this times 2, right? And if I have 4, I think the maximum we can put in a tube is 5, but I could have RRGG, and then R and B, then I would have 4, 1, 1, so it's also 6. So it doesn't really matter which configuration I have as far as the distribution of the balls is concerned. I may get more options on one tube and less options on another tube, conversely though. Right? So that's correct, that's always going to be 12, but if you pay attention to the video, then there's actually another 6 options that we have because, no, another 3 options that we have. Because we're allowed to reverse it too, right? Now here, if I reverse RR, I get RR, so that doesn't make any sense to do that, right? But the reverse operation also can only be done at the end of the search process. That's the last step. And once you reverse a tube, you're not allowed to unreverse it anymore. Or if you would, then it would not make sense. If you twist it over and then do some more moves, then you twist it back, then you might as well not twist it over, right? So the reverse operation would add another 3, because there's 3 tubes, each one of those I could reverse as an action. So our branching factor would be 3 plus 12, 15 all the time. So now what makes this problem interesting is that if you reason about it like that, then you think that, hey, actually, this is not very hard. I just start from my initial state and I apply these 15 different operators, right? Now I have a new configuration. Once we're here, I now have another 15 possibilities, right? Which will get me somewhere else. So let's say I do this, R. One of them will get me to RRG, GBB. Right? That is one of the successors there. And then this guy will also have 15 successors, 15 children. And if I do that for all of them, then eventually I'm going to reach the one that, let's say, BBRGGR. Maybe that's my goal. That's what I'm searching for. And now I found the solution. Then I just need to go through my tree, because we started the root, so we have a single node as a root. We would interpret this data structure would result in a tree data structure, a node with children, who again may or may not have children. And eventually I'm going to reach my goal. Once I found the goal, I'm done. So this algorithm is pretty obvious, right? It's not a very complicated algorithm to do. And in fact, you can think about this. This is for the Dr. Eureka game. But if you want to play chess, the same thing, the same approach should work. Right? Because I start with the initial position for chess, then I can make a move. And then it's a little bit more complicated because the opponent is going to make a move against me. But still, there's going to be a limited number, finite number of outcomes of the opponent making a move. And then I need to be able to pick my path through that particular tree. Or Sudoku. If you know the Sudoku puzzle, right, with the 9 cells, then my state would be the state of the puzzle. The actions that I could do would be if I want to represent Sudoku similar to this particular puzzle, then what will be my actions? Yeah, to put in a number, right? 5. So maybe I think there should be a 5 here. Then I can paint it and put in a 5, right? So then, how many, what will be, if this is my state, for reasons that will become apparent later on, how many successors, how many children would I have here? Well, that depends on how many empty squares I have. Because for every empty square, I can put in a number, right? So I can just pick one of the empty squares, and then for each one of those, so it's a number of empty cells multiplied by 10, right? Because for each one, multiplied by 9. Multiplied by 9. Because I can put a 1 or a 2 or a 3 or 4, 5, 6, 7, 8, 9. I can put one of those 9 numbers into each empty cell. So this will also result in a tree. It will be the same structure that we have. What is different is that here our branching factor basically remains constant at 15. Right? Every state we have 15 possibilities. With the Sudoku puzzle, it will vary, right? Because if I have 10 cells, now I put in one number, then I only have 9 cells left. So that means at the current level, I have 90 possibilities. At the next one, I only have 81. Because now I have 1 cell less, so I can put, at the next one I have 72, 63, so on and so forth. At the end, for the last number, we basically only have 1 cell, so then I only have 9 possibilities. So that's why when we discuss this kind of search-based algorithm, and we're trying to get a handle on how much work it is to solve, how long it'll take the algorithm to find a solution to that problem, we need to know 2 important features of the search. One is called B, the branching. One is called the branching factor, which is abbreviated as B usually. And as we've seen, sometimes that branching factor is constant, in which case it doesn't matter which level of the tree, I always have 15 possibilities. Sometimes it's dynamic, in which case you may talk about the average branching factor, or the maximum branching factor? With Dr. Eureka, that doesn't make any difference. It's always 15. The maximum, the average, the branching factor is always 15. But for Sudoku, it would change. And the other important part, the important feature that we need to worry about, is the depth of the tree. And that is usually abbreviated as D for depth. And the depth of the tree means how many steps does it take you. So this will be step 1, here's step 2, and here's step 3. So in this case, our depth will be 3, right? Before we can find a solution. How many moves do we have to make before we can solve the puzzle? Now, again, in this case, I guess it's reversed. For the Dr. Eureka, it depends on what the target configuration is. Maybe I can reach it in one move. Maybe it will take multiple moves before I can reach it. But the depth is not constant. Here in the Sudoku puzzle, if there's 12 empty cells, then the depth is constant, right? I cannot possibly solve the Sudoku puzzle by just putting in 3 numbers. I must fill in a number for each one of them. So then the depth may be variable. So again, we could discuss then our worst case or maximum depth and our average depth. If you're dealing with domains where this actually is variable. Now, if we're doing this expansion with the tree here, and I start with a node, and then I have B successors, then how many nodes do I have at this level? So if this is level 0, at level 0 I have 1 node. Here I have 1 node. At level 1, how many nodes do I have? Level 0. Level 1, I have how many? 15. But if it's B, then if it's Sudoku and I'm making a variable instead of 15 for Dr. Eureka, then it will be B, the number of nodes that I have, right? Because I say on average I have B children. Here I have 1 node, so that node will have B children. So at this level I will have B nodes. Then each one of those will generate new children. So at level 2, how many do I have? B squared, yeah. At level 3, I'll have B cubed. Before I find a solution, how many nodes will I have in that level where I actually find the solution? B to the power of D, because we assume there's at least one step that we need to make. Now, if I want to estimate the amount of work that I need to do, then this number, it's important to realize that this number here is actually just the level, the nodes at this particular level. It does not include all of these nodes, right? But never mind, for reasons that we'll go to in a little bit. We only care about the number of nodes at that particular level. So the problem with this algorithm is that if I want to have a robot and I look at the number of motions that I need to make with my arms, right? You see, like, the robot moves there, all these kind of motions, move there, twist the thing. Then there's about 100 motions that it needs to do before it completed the puzzle, right? And this is at the motion level. So if d is to the 100, and now our complexity here would be 15 or 7 or 8 or 18, 15 plus 3 if we allow for swapping things, right? Let's just say, okay, we don't care about the swapping, we played without the swapping. Then our complexity would be 15 to the power of 100. So you run your program and you test it out, and you test the simple scenarios. So with 3 steps, things are working good. If the solution is within 3 steps, it'll take you 1 millisecond to calculate the solution, right? And if it's 2 steps or 1 step, it's even faster than that. But you tried it out in your testing, you figured out that on the particular computer that you're using, things are good because you can calculate 3 steps and it only takes 1 millisecond. So, okay, 100 is a bit more than that, but you're still hopeful that you will be able to solve the problem. So assuming that your computer can search up to level 3 in 1 millisecond, how long will it take to search up to level 100? What do you estimate? Or better not estimate, but actually calculate what the amount of time would be that it would take in order to search to level 100. And this approach, this idea, you need to write a computer program to do that unless you are really good in calculating things in your head. By the way, but this idea that, we can do 1 millisecond, so the larger problems, the real world problems, we can just solve by having a fast search method or faster computer. This was the main philosophy of artificial intelligence up to the early 90s. People thought this is it. That algorithm, that search algorithm, maybe a little bit smarter search algorithm, because sometimes it's a graph, not a tree, and then we can combine things. We consider the approach to solving artificial intelligence problems like puzzles, planning, motion planning, path planning, logistics planning, medical diagnosis, case law, mathematical proof, reasoning. All of that was considered to be just one example of a search problem. And they all are. You can actually map them to a search problem. So all we had to do is find a fast way to search that space. So now let's have a look. So here's another video. This was slightly earlier from our robot. But now let's just see, our branching factor is 15, right? And our expansion speed, the speed of our search, would be nodes per second, so b to the power of 3 divided by 0.001 second. So this is about 3 million nodes per second, right? Very, very fast. Usually in an AI system, you have about 1,000, 10,000 nodes per second. But here, okay, 3 million nodes per second. So how long will our algorithm run? B to the power 100 multiply the nodes per second. So divided by the number of nodes per second. So this is the number of leaves, b to the power of 100. And our time t would be the number of leaves that we have divided by the nodes per second. So our algorithm would run for this many seconds, which doesn't really look so bad. 1.2 times 10 to the 111. So that's the number of seconds. So this many seconds in an hour, right? So this would be the number of hours that our algorithm calculates. Okay, then there's 24 hours in a day. Okay, so then 24 hours in a day, 7 days in a week. But I'm going to skip ahead. 365 days per year. This is how many years we would be calculating. This is the number of millennia, thousands of years. Actually, thousands of years is not going to do anything to that number. This will be millions of years. This will be billions of years. How old is the universe? Our physics guys? The estimated age of the universe? 13. I heard 13, 14 billion years. So the universe is 13 billion years. You're trying to calculate for 3.8 times 10 to the 94 ages of the universe time period, right? So this is completely impractical, that kind of algorithm. My physics colleague, he told me that 10 to the 80 is a number to keep in mind if you're trying to estimate complexity. 10 to the 80, I've been told, is the number of estimated primitive elementary particles in the entire universe, right? So elementary particles, proton, neutrons, electrons, right? There's bazillions in this cup here, in this plastic thing, right? Bazillions of atoms, and they each one have multiple electrons, protons, and neutrons. So then this is this cup. Then you think about all of Earth, all the mass in Earth. And then the Earth is the solar system, right? The entire solar system, Jupiter, much bigger than Earth. The Sun, much bigger than Earth, right? Then we're a tiny fraction, a minuscule fraction of the Milky Way, which is the galaxy that we're in. Then we have billions and billions of stars and bigger stars than the Earth, than the Sun, in the Milky Way. Right? Then we have other galaxies, Andromeda and what have you. And then there's billions of galaxies. And all of this mass, if you find the electrons and neutrons, you get to a number of about 10 to the 80, which means that if your algorithm, ours is 10 to the 94 ages of the universe, right? So that means you're trying to paint every electron, neutron, and proton in the entire universe before you come up with the answer. This is not realistically going to give you an answer unless d is very small, right? That's why your simple tests work. If d is 3, then it's not a problem. If the 4, you can count it. But if you look at the runtime of this algorithm and you plot the runtime versus the depth, then the curves all look like this. Eventually, you hit a wall, and this particular wall, there's no way to overcome that by saying, oh, maybe I can use a faster computer, right? Doesn't matter, even if you have a computer that's a billion times faster, a billion times faster, then you could cut off 18 out of the 10 to the 94, which is not enough to make a blip in the possibility of solving that particular problem. Not a hope. So there's just no way to get over this complexity wall. If you say, oh, but I can use a GPU, I can run 1,000 in parallel. You can run billions in parallel. It won't make any difference to the complexity of the chance of solving a problem of size 10 to the 100. The only chance that you have would be, for you guys, if you use a quantum computer. If you have enough bits and you can all entangle them, then you could solve this. But it's not clear if we will ever be able to keep that entanglement stable enough to be able to do the computation. So quantum computers are still out there. But if they actually would work for like gigabytes of state space, then yes, then this whole AI lecture would be irrelevant, because you just run an infinite, you just run 10 to the infinite computations if you want to. Because of the weird way that the particles interact in the quantum world. And there's also some theoretical limits on the quantum computation, but people don't really know what they are yet. So, luckily for us, our Dr. Eureka game is much simpler, and in particular, our depth is quite a bit smaller than that. We'll try and calculate what the depth limit is for the Dr. Eureka game. But let's try and implement a search algorithm then that can solve the Dr. Eureka game, and you should do that yourself. So the class is very much participation based, I hope. So bring your own laptop with your own Python environment. That would be the best. If you you didn't bring your laptop, then you can open the Google Collaboratory and you can try and implement the solution that way now. So I give you 30 minutes to implement a planner system that can solve the Dr. Eureka game. And then tell me, the question would be, of course, to find the plans, but the question would be, how many different states are there actually in the Dr. Eureka game? And I will just do my programming here, but don't look so much at what I'm doing, but try to find your own solution in Python. Two functions that you need. If you implement your search, usually there's a goal function to specify whether a particular state is the goal or not. And secondly, you need to have a function that generates all the possible successors. Those 15 children, you need to have a function that can calculate those 15 children given a parent state. So there's different options for representing your state. I just decide to use instead of a list of lists, I just make it strings because I can index strings and it makes it easier to print them out. That's the only reason. It'll look a little bit nicer if we print it. So tube 1, tube 2, tube 3, and more, I think it's simpler to then say that the first element of the bottom element of the tube. Because otherwise, if I have, this one is bad, let's pick R, oh, G, B, G, and then I have too many B's, I need another R. Like this. I need to know whether RG means red is on the bottom, green is on top, or green is on top, red is on the bottom. I just have to figure out some convention for that. So if I have that kind of configuration, then I can implement my, what's usually called the successor function, or I can call it the gen_children function. So here's some state. And one of the things that I need to do is, because I need to generate children, right? So I can generate a list. So I want to return a list of children, and the state that I generate, I need to make a copy of it, because state is a list, so that is passed by reference in Python. So if I change state, it'll actually change the state everywhere. But I want to generate a new state, right? One that is independent. So that means I want to generate this as a copy. And I can use Python list comprehension to do that, or t.copy. State.copy. We'll make a shallow copy of the list, which should be enough for this particular task. Now here, this only works if from and to are different. Otherwise, I just ignore it. I'll just skip it. And then for number of balls in range, starting at 1, because I need to move at least one ball, and the maximum number I can move would be the length of t from. And then, so now I need to take NB balls from t from and put them in t2, but because I pour them, they have to be reversed. So that shouldn't be too difficult, right? S t from is equal to S t from, and I start from the end. So I start at 0 and I go up to the length of from minus NB. That should actually do it in Python. And S of T2 is equal to S of T2 plus S T from. And here I can use minus NB. Minus that would be length of, it should be minus NB dot reverse, if that exists for strings, I'm not sure. No. So here I can reverse this. So that's done. Then children dot append S. And return the children. So let's test that out. So let's take a state, RR, GG, BB, and children, generate the children from S. Print the state. And then print children for C in children, print C. Let's see what happens. It's not length of T from, it's length of state T from. Yes, T from. Right? Default. Yes. That means from minus NB up to the N. NB. Or NB in range, starting from 1. And that is minus, so why is that not the same as this? From which is minus 1. And for this minus 1. If I use, no. NB. Doesn't seem to minus 1. Yeah, it doesn't come. It doesn't like that. Okay, it should be the length of S T from minus 1 minus NB up to the end. Actually, let's change this to because later on I may want to change that to variable number of tubes. Oh, that's why it failed, because I forgot to put in the comments. So I can move one red one, I can move one green one, I can move one blue one. From 0 up to this -1. So here I need the +1. Okay, so the problem is the strings aren't copied. So we need to go yes for yes out copy. Two, column 2 for 2 bit state. I can copy those. I need to generate the state here. And now we can move one red, then we move, can move the greens, and then we can move the blues. And we can move one red first to the first tube and then to the second tube, or both to the first tube and the second tube. So let's check this one here, the reverse part. I'm pretty sure this should work with just minus Let's see what reversed. There's no function to reverse the string in Python. Oh, okay. We can use reverse slicing. I didn't know that was even allowed. So he have one red, then we get GTR, or both reds, and they're gone. BBR, that's correct. Wrong. G. One G, two there, two. Now the T2's don't work. D. One is wrong, minus two. Length of S. From minus B. Reverse. Because and that should be state, not and it should be state too. And let's make this a state. So we cannot work on our copy, we have to work on the original state. minus 1 to the n should be 2 plus zero to minus 1 should be 1 to the why do I have none? Minus NB minus 1. Okay, that's correct. Yes, now we have RGGB, now it works. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 11, 12 successors, which is without any flips. That's what I would get. I can also add the 3 flips if I wanted to. So for t in range length state, s is equal to state of copy, and then s t is equal to state t minus 1. Children dot append s, and now of course with this setup it doesn't actually matter because RR reverse is still RR, so I have to use a different initial state. So let's go RG, G, B, B, R, and see what kind of children we can get. Now I have 1, 2, 3, 4. Actually, I can just print the lengths of the children. 15, and here we have RG, so if I flip the first one I get GR, GD, BR, or BG, or RD, that's the ones that I can flip. Now, let's worry about the successor here being only able to do that at the end, later on. Right now we're just checking to generate our search function. So I have generating the children, then next would be specify the goal. So here I need to specify if I have a goal state. And of course that can have different versions of that. So let's specify that right now we're just searching for a particular state that is a goal, so the state is equal to, and then what I want is RR, or we reverse them, BB, GG, RR. And then we actually have all the parts in place in order to implement a search algorithm. We can have an initial state, and then search that initial state. And I probably want to add some more parameters later on, but that will be my solution. I pass in an isGoal function. Now I haven't written the search yet, so let's call it Dr. Eureka search. Actually, let's not, because that search algorithm now will work with any function. So I have a state, I have a genChildren function, I have an isGoal function. And then let's see, I define a queue which initially just contains the state, but with the state I need to pass in some additional information, so later on I'll expand that. Then while the length of the queue is greater than 0, so while I have an element, I pop the element of the queue. generate all the children. First I need to check if it's a goal, then yeah, return the solution. We need to do some more processing with the children later on, but for now I just go through the children and I add them into my queue. Or queue.insert at index 0, I want to insert the child. It's not gen success, it's gen successors. What do we call that function? Oh, it was C and children. Index object. It doesn't return it, it's just insert. Now it's actually searching for a solution. It should be searching for a solution. Could it go around in circles? So whenever we're implementing a search like that, that's one of the problems. That's why we need to make sure that we're not actually generating a state that we generated previously, otherwise we end up in an infinite loop. But that shouldn't have happened in this case because I insert the children. So let's just print the cube. Stop sending output, but should have at least sent something. We stop the loop if we expand it more than this many number of nodes, and I can pass that in here. I just want to generate 20. Increment our node count here. And then this is what we get from RGGBBR, GGBRB. So it flips. Of course, and then it can flip backwards and forwards. So I thought turn off the reverse ones. Two, one. RG, RG. One. Multiple there. And my goal state was BBGGRR. So let's start with simple one, BBGGRR. BBGGRG. I think I started with GGR. Yeah. here I picked the wrong one. BBGGR. If I move one, it should be RR, not RG. So from so the state that I have is this one. BB, one blue one there. Minus 2, minus 1. We'll take it from state. Zero to negative 1 to negative 2. And I get GGR plus minus 2. I don't reverse. That'll give me the BB. Okay. So the minus 1 seems to not work correctly. C for C in reverse state, this dot join to get the list. It's reverse. So 1B, 2Bs, 1B, 2Bs. Okay, so now that works. And I can generate a search state and here. The solution is and here it finds a solution already because it's only one level that it needs to do. And now the tricky part, of course, is we're usually not just interested if there is a solution. We would also like to find, so until next class, you could figure out how to generate the history of the states so that you can actually print out, like move 2 from there to there, move 1 from there to there, that kind of thing. So that's you can do as a little homework until next Monday, and then I'll see you next week.